All right. So we have 2 moles of iron 3 oxide plus 3 moles of carbon, and that's going to produce 4 moles of iron and 3 moles of carbon dioxide. Okay. So it says you have 0.48 moles of carbon. How many moles of iron 3 oxide are we going to have? So we're starting with the 0.48 moles of carbon. And according to our ratio, if we have 3 moles of carbon, we're going to need 2 moles of iron 3 oxide. So if we have 0.48, we're trying to figure out how much of this are we going to have. So we're going to divide by 3 moles of carbon, and we're going to multiply by 2 moles of the Fe2O3. And so 0.48 times 2 divided by 3 is going to give us 0.32. And that's mole of the Fe2O3. All right, so now it says a student produces 7.5 moles of iron. So that's what we're starting out with because that's what's given in the problem. It says their lab partner tells them they need to know how many moles of carbon reacts with excess iron 3 oxide. So the question here is, what are we trying to figure out? What are we trying to figure out for the product? I'm sorry, not the product. What are we trying to figure out for what we're getting into? Here we had carbon, and we got it into iron 3 oxide. What are we trying to get it into in B? The iron 3 oxide? Okay. What does excess mean? Yeah, what does an excess reactant mean? That's the leftovers. Does the excess reactant make the theoretical yield or make any product or anything? No. So do we care about the excess reactant? No. We do not care about the excess. Well, so if you have 7.5 moles of iron, what are we trying to make? Let's read it again. It says a student produces 7.5 moles of iron. Their lab partner tells them they need to know how many moles of carbon reacts with excess iron 3 oxide. So what are we trying to get this into? Carbon. How many moles of carbon react with excess iron oxide? So what is carbon in this reaction? No, what type of reactant is it? If this is the excess, what is carbon? Who said it? Someone said it.
Limiting.
Did you say it, Olivia? The limiting. Yeah. It's the limiting reactant. So the limiting reactant is the only one we care about. We don't care about the excess because that's never going to make our product. The only thing that's going to make our product is the limiting, because what happens with the limiting reactant? It makes the total amount you can make, because what happens after that amount has been made to the limiting? You can't make any more because you're out of that limit, you're out of that product, you're out of that reactant. Yeah. So the limiting is all we care about. If it says excess, just cross it out. We don't care about it. So we're going to carbon. So now go to carbon if you haven't done so already, because I bet a lot of you could do that. We need to go from iron to carbon. Do that on your paper. We need to go from iron to carbon. So if we have 7.5 moles of iron, how many moles of carbon would we have? If you haven't done that yet, do that right now, please. So if we look here, we're going to need 4 moles of iron, and we're going to need 3 moles of carbon. And that should give us 5.625 moles of carbon. So this last one right here, this last one says your teacher gives you 23 moles of the iron 3 oxide, which we now know is our is the excess. But so we have 23 moles of the iron 3 oxide. We want to know how many moles of carbon dioxide and how many moles of iron we could produce. So how many problems do we have to do here? We have to do 2. Yes, we have to do 2 problems. Let me move this a little bit here. So we're starting with 23 moles of iron 3 oxide, which is right here. And we want to know how many moles of carbon dioxide and how many moles of iron we're going to produce. So if we're going to go from iron 3 oxide to carbon dioxide, that's a 2-to-3 ratio. So 2 moles of Fe2O3 to 3 moles of CO2. So that's 34.5. And we have to do 23 moles again. Fe2O3. And this time we want to go to iron. So that's a 2-to-4 ratio. That's going to be 46 moles of Fe. So if we have 23 moles of this, we can make 46 moles of iron and 34.5 moles of carbon dioxide. I know, it's a lot, isn't it? All right, here's the problem, my friends. Can you measure moles on a scale?
Yes.
Well, how would you do that?
By using grams.
By using grams. So we have to know how. We know how to get one thing into another thing now using the mole ratio. But we have to do grams on either side of it. Turn your page over.
Wow.
All right. Grams to grams. Grams to grams. I like to think of it as a gram moly sandwich.
What?
You'll see what I mean in a moment. Like a moly center. Yum.
What?
Probably not. Okay. So it says how many grams of oxygen. So we want to know how many grams of this are required to burn 3.6 grams of carbon monoxide, which is this.
Interesting.
Okay. So I've actually written the steps out for you right here as we go through them. Okay. The first thing we have to do is convert grams, because to be able to do the mole ratio, right, to get from CO to O2, we need to get this into moles. Because we want to convert this into this, so we have to get this into moles. So we're going to take 3.86 grams of CO, and we need to get that into moles of CO. You guys have done that before.
Yes.
How do we have to do that? How do we do that? We have to get the molar mass. Yes. So carbon is 12.01, and oxygen is 16. So I get 28.01. Is that going to go on the top or the bottom?
The top.
The bottom.
Oh.
Grams of CO. And that's 1 mole of CO. Okay. Now, grams canceled, leaving us in moles. But now that we're in moles, now we need to do our mole ratio. So if we look, we have 2 moles of CO and 1 mole of O2. So 2 moles of CO is going to go on the bottom. And 1 mole of O2 is going to go on the top. Moles of CO cancel. See why you can't just be like, do I multiply or divide? You might want to write stuff out with units now. All right, so now we're in moles of O2. What are we trying to get it into, though? Grams of O2. Can we get moles of O2 into grams of O2?
What is this?
I know, right? Now we need the molar mass of O2. 16 plus 16. 32. Right? So if we have mole up here, what's got to go on the bottom to cancel? Mole of O2. Gram of O2 on the top. Where is the 32 going to go? The top. Moles cancel. So we're going to take 3.86, divide by 28.01, divide by 2, multiply by 32, and you should get 2.205. We're going to go 3 decimal places. Grams of O2. Isn't that nice and pretty? It is a beautiful thing, people. You now know you could have 20 grams of this, and you could figure out how many grams of oxygen you're going to need. Or you could have 0.5 grams of this and figure out how many grams of carbon dioxide you're going to produce. It's all converting. Isn't that crazy?
Yes.
Ooh, let's do B. Let's do B. Okay. All right. So we have 65.9 grams of oxygen gas. We want to get into grams of carbon dioxide. So we're going to do 65.9 grams of O2. We need to get grams of O2 into what, class? Moles. So grams of O2 on the bottom, moles of O2 on top. Oxygen is O2, so it's going to be what? 32. And that's 1 mole. So grams of O2 cancel. And then we need to do our mole ratio. So we look up here, and we know that we have 1 mole of O2 for every, this time we want carbon dioxide. You see how there's a di right there too? So we want 2 moles of CO2. So we're going this to this right now. So we want 1 mole of O2 and 2 moles of CO2. So mole of O2 cancels. And then we need to get moles of CO2 into what? Grams. So mole of CO2 into grams of CO2. And the molar mass of CO2, we're going to take 12.01 plus 32, because O2 is 32, right? So that's 44.01. Does that go on the top or the bottom? 44.01 grams for every 1 mole. Moles of CO2 cancel. So we're going to take 65.9, divide by 32, times by 2, times by 44.01, and you get 181.266.
Wait, how did you do that? You did.
65.9, divide by 32, times by 2, times by 44.01, and you get grams of CO2. Want to try and do it by yourself?
No.
Oh, sure. Top one. Did you
Don't.
just divide across